Good afternoon, everyone. Good morning to those who join from the West. We have some participants that are, at least that I know, from Brazil. So bom dia. We're happy to have you. We're quite excited. My name is Stefan Urovich. I'm one of the two co-founders of Space Tech Partners, a Brussels and Munich-based consultancy that has been entrusted by the European Space Agency to deliver the AI4EO project, which, as you know, consists mainly of organizing challenges. So we're extremely excited because, well, we're going to announce after 4 months of activity, intense activity, I would say, announce the winners of our first challenge. And we're going to also lift the veil over our second challenge. So we're really happy that so many of you are here, so many in particular of the participants. We hope that you enjoyed this challenge. We do recognize it was a very tough one. We didn't start organizing challenges by doing really small and easy ones. There was quite complicated data sets, 3 AOIs, 2 different atmospheric composition variables. So quite a challenge. And we were absolutely enthused by the fact that there were so many participants. We had, I got that noted here. We had at the very end still 7 teams that were competing in the last miles, but we've had 264 registrations on the platform, 173 active participants, 113 teams were created. Some of them submitted results, and as they would never climb the leaderboard at one point, apparently they decided to quit. But again, 7 teams continued to fight until the very last minute for the 4 prizes that we're going to be awarding today. So we're quite amazed by the result, and we really want to thank all of the participants and all of the partners of the project for the hard work and for the interest and effort put into this activity. So without any further ado, I'd like to pass on the virtual floor to our 2 keynote speakers. The first one will be Klaus Zehner. Klaus is the mission manager for the Sentinel-SP Copernicus satellite. What is a mission manager? It's a very important person for a satellite because it's the person in charge of ensuring the liaison between the community of users, so those who are going to use the data to develop applications or to develop science, and the European Space Agency. So we're very honored to have Klaus here. Obviously, the Sentinel-SP data was among the key data that was used in trying to crack the challenge. So Klaus, the floor is yours to let you know what are your takeaways of these 4 months of competition.
Okay, thanks for having me invited here. And it's really, I hear with great pleasure that there was such a high interest in this competition because measuring air quality from space is really changing now with Sentinel-SP, and I will show you some results on this. And it's clear that you can still work much more on this data. We are providing some information like aerosol information, but we do not provide the information that is really needed by the end user, which is particulate matter. And so it's really very important for me as mission manager to see how our data are being used and are further developed to make them even more useful for users. So I will give a short presentation on the latest results on Sentinel-SP air quality measurements. Few words on the mission. Sentinel-SP Precursor is the first atmospheric Sentinel mission. It was launched during October 2017 and has been working since this time really very well in operational mode. I'm not going much into detail. What is really new as compared to previous atmospheric satellite missions measuring air quality from space is the high spatial resolution. Just below the satellite, you have a spatial resolution of 5.5 times 3 kilometers, and you get global coverage within 1 day. Other satellites that are still flying, like GOME-2, has a spatial resolution of 60 times 30 kilometers. So having this information, you really see that with Sentinel-5B, you're getting much more detailed information based on the spatial resolution, and you have global coverage as well. So this is really a new satellite providing new data sets that can be used for operational applications, which is the key issue for the Copernicus program. Key objectives of the missions are provide information about ozone, air quality and climate monitoring and forecasting. Jumping now to air quality, we have been and we are still affected by COVID-19. So what can you see with the Sentinel-5B from space on the impact of COVID-19 on our life, but also on air quality? From ESA side, we issued during 2020, during March, it was a video, I'm just showing here some still images, showing how air pollution has changed over China before COVID and during COVID. And what you really see that a nitrogen dioxide concentration from space, they give an indication about industrial activities and emissions coming from traffic. And you really see this huge difference when you look at average the data here in the range of 2 weeks during January 2020 to March 2020. So you really see the impact on air quality from space based on COVID-19. So this was more or less a public relations story, but now going a little bit into detail and to move from China to Europe. We also looked how the situation was in Europe, and also here we're using averages, and we compared data from 2019 to 2020, and we tried to use data that had similar climatic situation. What we found out in this study was really to look at the uncertainty of this data. It's one issue to provide nice images for public relations, newspapers are picking them up, but how can you really use them also for applications like inventory monitoring? And for this, we had a detailed look, colleagues at KNMI, like Henk Eskes, what are the errors of this data? And looking at some cities over Paris and comparing the time periods before COVID and during COVID, we saw a decrease of air pollution based on COVID in the range of 50%, with an error about 15%. So it's a huge signal, but there's also quite some error. And this is really mainly caused by the weather. This was a key outcome here. But just to say that beside public relations, we also did some science. What is the situation right now? Here you see a similar image. Again, averages. These are monthly average, 2019 in February, 2019, 2020, and 2021. And you really see pre-COVID area over China, COVID area, and again, the situation a few months ago. And you see how this is changing, and emissions, air pollution is quite normal again as before COVID-19. But you really see this from space, and this is just a powerful message that was really picked up also by the newspapers and by other news agencies. Based on these results, we have been asked by the European Commission to provide a specific service, not only on air quality, but also on other indicators, how COVID-19 are impacting our life. And on air quality, we used NO2, like I've shown before. What is specific for Sentinel-5B, for the TROPOME instrument, you have a broad wavelength range, and you can derive other air pollution measurements, not only nitrogen dioxide. And here again, just another example, it's sulfur dioxide over India. Again, pre-COVID situation and then during COVID. And you really see also a big change of emissions in the range of 40%. And what is also specific, you see some places where you have the same emissions during both time periods. And these are places where you have caloric power plants where coal is being burned in order to generate electricity. And for these specific hotspots, you see more or less the same emission. And we studied a little bit more in detail. The electricity production only decreased during COVID time by 10%. And we see the same also in the emissions from space looking at sulfur dioxide. This is just another example on how sensitive these Sentinel-5P drop ohming measurements are. These are the first ever measurements from space where you see emissions of nitrogen dioxide concentrations from a single ship. Here you see the ship track. Here you see, based on the wind, how the emission plume is moving, and the colors are indicating the concentration of nitrogen dioxide. Overseas, there's a specific situation. We're using measurements during sunken where you have high reflectivity, but I'm not going into technical details here. The key message here is with Sentinel-5P drop ohming, you can measure the emissions of nitrogen dioxide of single ships. What is even more interesting in the future is sulfur dioxide, but that's another story. As I've mentioned before, you can measure different air quality species with drop ohming Sentinel-5P. Here, just one example on looking at the emissions coming from fires. What you see here, you see nitrogen dioxide. Nitrogen dioxide has a lifetime in the atmosphere about several hours, especially during summertime. So you really see, looking at this image, where the information is coming from. Looking at another species like carbon monoxide, has a longer lifetime in the atmosphere, you see how this air pollution is moving. And you see how CO is moving from one country in the US to another, but also even from one continent to the other. And that's also a power of satellite measurements as compared to ground-based measurements, that you can follow the movement from one country to the other, even from one continent to the other. And you get other information and you can use them in synergistic way. My last slide. So with the Sentinel-5P, we could really demonstrate that the satellite measurements can be used to monitor impact of COVID-19 on air quality. But it's also clear that these satellite data have to be used very carefully. We were contacted by journalists. They looked at our data by themselves. They used the daily measurements that you can find on the web of nitrogen dioxide. They are not really so useful. You have to be careful. We used averages in order to reduce the random noise. And we developed a specific tool. We called it Sentinel-5P Product Algorithm Laboratory to provide these averages to users. And you can find here the web link where you can find these 2 weekly averages of nitrogen dioxide. As shown just on the example of fire emissions, Sentinel-5P provides several species on air quality that can be used in a synergistic way. Now coming back to this challenge again, it's really great to hear that our data are being used and are further investigated, brought to another level to make them more useful for users. And I'm looking forward to the other presentation. Thanks for your attention.
Thank you, Klaus. The second keynote speaker is Vincent Ripoc. Vincent Henri, is the head of the Copernicus Atmosphere Monitoring Service at the European Center for Medium Range Weather Forecasts. So the ECMWF, this organization, is entrusted by the European Commission to deliver 2 Copernicus services, the Copernicus Climate Change Service and the Copernicus Atmosphere Monitoring Service, which he heads. They also deliver critical results from modeling to the Emergency Management Service. So ECMWF is really one of the spearheading organizations in the delivery of Copernicus services. Vincent Henri, we're particularly grateful to him because, in fact, he is one of the janitors, or the janitor of the, and I don't say father because it's not correct anymore. So the janitor of this challenge. We turned to him when we were looking for bright ideas and really intellectually challenging ideas for our first challenge. And he came up with the concept was derived into a challenge. So we're very, very grateful to him. We're honored to have him as a keynote speaker. We're grateful also for the support that ECMWF himself and their also AI experts, because they are also in that domain at the forefront of investing to use AI not only to support numerical modeling, but also forecasts and all kinds of analysis that are useful to both meteorology, climate services, and atmospheric monitoring. So Vincent-Henri, thank you again so much for all the help you've provided us with, and the floor is yours.
Thank you, Stéphane. So I didn't prepare slides. I just want to say a few words to say how happy I am today to attend the event, the award ceremony for the first challenge AI4EO. And I remember actually very well when we discussed with Stéphane and Catherine and the team the ideas about this challenge. At that time, well, it was a long time ago, actually. We were traveling a lot, and I was at the AGU in San Francisco, and we had arranged a very early phone call for me in San Francisco, which was good because of the jet lag. And we started discussing what could be an interesting challenge in the area of air quality. And my answer, based on the experience we have in the Atmosphere Monitoring Service, is that downscaling the products that we provide is really the key challenge. And if you want, the raison d'être of lots of activities that many of our users, whether they are commercial users selling platforms to inform about air quality, or public institutional users like the WHO, the WMO, or UNEP, trying to estimate the so-called global burden of diseases, the number of excess deaths that are caused by inadequate air quality. And all that boils down to downscaling. So what we do in the Copernicus Atmosphere Monitoring Service is to use observations and of course, primarily the observation of Copernicus, and Klaus presented Sentinel-SP Precursor, which is, I would say, our crown jewel in terms of atmospheric composition monitoring, but also other types of data. And what we do using models and techniques such as we call data assimilation, we provide 3D fields of atmospheric composition. So it means that we can relate directly to surface concentration, which is what people breathe and actually what has impact on health. However, in order to do that, we need to represent the world in terms of small cells, but the cells that we can afford to do, they are pretty coarse. It's typically 10 kilometers at best. And the reason why it's 10 kilometers is not only because of a computing limitation, it's also because we never have enough observations to fill, for instance, say a 100 meter by 100 meter grid that would cover Europe or that would cover the world, because there are not enough observation. As Klaus mentioned, even for Sentinel-SP Precursor, if you want to have an accurate picture, you need to average over a number of days so that meteorology and the presence or absence of clouds can be taken out. So that's the reason why we deliver fairly coarse resolution products, and there is a room for downscaling. And in order to do that, traditional deterministic approach are not best suited, because you don't have enough observations, you cannot initialize everything properly. And as opposed to that, AI is a technique of choice to use this coarse resolution information, use higher resolution information that comes from satellites, so Sentinel-SP, but also much higher resolution imagery to come to find enough resolution to serve communities that work in the area of impacts and prominently health impacts. So this challenge is a real life question. It's not something that has been invented just for the purpose of entertaining a group of enthusiasts of artificial intelligence. It's something that has a future. It's something that we will look very carefully, both in terms of public application or maybe commercial applications. I was so pleased to hear from Anne-Catherine and Stéphane that all the success that the challenge had, and that so many teams kept in the competition and went to the real final shoot down here. It means that there will be a number of solutions for going forward with this problem. And yes, I'm very happy to be here. I'm very keen to see some of the best outcomes of the challenge. So thank you very much. And yeah, I'm all eyes and ears to follow this award ceremony.
Thank you, Vincent-Henri. Thank you very much. Well, now I think what you're all waiting for, or many of you are waiting for, which is the award ceremony. The time has come to get to that. So I will now pass the baton to Nicolas Longepé. He's Earth observation data scientist at the PhilLab of the European Space Agency's Earth observation division. And he's the project manager for the AI4EO projects, and the counterpart of my colleague Anne-Catherine Debien, whom Vincent-Henri has been talking about. Unfortunately, she had something she could not avoid today, so she's not with us, and she's asked me to sit in for her. But they've been working with Nicolas in ensuring that this project is hopefully well run and that the challenges are a success. So Nicolas, the floor is yours.
Thank you very much, Stéphane. So it is indeed the time to finalize this challenge and announce the winner. So it has been, as Stéphane mentioned, a very exciting performance where actually many teams registered, look at the data, played with it, and submitted some nice solutions for this challenge about downscaling. So two variables, the fine particulate matter as modeled by CAMS, but also the nitrogen dioxide measured by Sentinel-SP. So I guess it was a really challenging challenge, I would say, and I'm glad to announce now the different winners. Before that, I'd like to recall that so the top 3 teams and their member, as well as the winner of the Special Student Prize, will get AI4EO points that will be used to pick as you please some prizes. So it will be as a first come first served basis. So starting with the first place, the second, the student team, and then the surprise. For this challenge, we had the nice contribution from different sponsors, starting from Airbus. We granted the 10,000 euro worth VHA imagery. We have 2 years of processing environment and some training by Wakeo. We have 3 GPU cards from NVIDIA, which is Quattro RTX 8000. Not to forget many other vouchers for scientists, technical or business consultation from the different partners that you can see on the left. And also some DIAS access from Honda, Mundi, and so on. So many thanks to all the sponsors. It was very nice to have you on board. So I like to remind the final ranking is based on 2 criteria. I mean, we have the quantitative leaderboard, which you know, and we had also a jury evaluation that evaluates all the submitted files and the different approaches. Having said that, so let's start then with the surprise, which is given to TSSA AI teams. So many thanks to you and congratulations to these teams. So actually this team is composed of 2 guys and 2 research engineers from Precursor, which is a private public companies in Navarra, in Spain. So we have Christian, which is a machine learning engineer at Precursor and working towards a PhD in AI. And we have also Javier, who is a data scientist at Precursor as well. So with some experience on working on IT and service industries. So many thanks to you, and you win 10,000 points that you can use as you wish in the catalog. Yeah. Then we can move to the student prize, which goes to Zita, congratulations to you. So it's very weird because I speak only to my screen. So I hope that anyway, so actually this team is composed by only one guy, which is called Rao Shapke, and with an undergraduate student in computer science at the Federal University of Rio Grande do Sul, so in Brazil. So we are very pleased to see someone from Brazil winning this. So as mentioned, the aim of this organized challenge is also to bridge the different gaps between the communities. So having a student in computer vision from Brazil working on an AI challenge around European-based data satellites and also model is already a great success. So we are very happy about that. So I'm sure, I hope at least you will make good use of this 10,000 point that you won today, and you can use it to get some access to data, computing, and consultancy from a wide range of European experts. So many thanks again to Rao for participating, and congratulations again. Then we can move to the second place, which goes to the team from Agenium. Many thanks to you, and congratulations for sure. So Agenium, actually, this is a French company based in Toulouse. They offer expertise in the field of Earth observation and deep learning in two areas, space mission and multi-source downstream services. At the PhilLab, we know them very well. We have a very good partnership with them. So in space mission, their skills cover onboard processing, as well as image, ground segment, and spaceflight dynamics. So many thanks to all the team, Nicolas, Adrien, François, Emmanuel, and Rosa, all from Agenium. Many thanks to you, and many thanks for being very active during the challenge. Last but not least, and this is the most important, is the winning team, and it goes to Assign WASD. Congratulations to all of you, and on behalf of all the team partners and sponsors of this challenge, we are very happy to have you won this first challenge. So actually, this team is composed of 5 people: Andrea, Cristiano, Marco, Carola, and Linda, from 3 different entities. We have Assign, which is a privately held company in Italy, in Genoa, in it. And we have also Fade Out Software, which is a software company with many years of experience in the observation sector. They develop the WASD platform, which is a cloud platform for processing Earth observation data. And finally, this team also integrates 2 students attending some master degree in computer science, and with Carola and Linda. So many thanks to you, and congratulations. I guess now you can have a few words on maybe your solution. You can also introduce yourself. Before we move to that, I'd like to say that well, this challenge was very great. I mean, we saw more than 200 teams, people registered with 173 active participants. We have more than 1,200 solutions that was submitted during the four months of the challenge. So I guess many thanks to all of you. We'd like to thank again the sponsors, Airbus, NVIDIA, Wakeo, and so on, for your nice contribution to this one. So maybe, SNYSD, if you can, now the floor is yours, and maybe you can take the lead on this, and maybe just present yourself and give an overview of what you submitted. That would be great.
Yeah, good evening. I'm Andrea Rapuzzi. We are really happy and proud and honored about this challenge. I will briefly present our solution, and then Cristiano will tell another couple of words about this. So our solution, is it possible to share my screen, or I can go even without slides?
Yes, it's possible to share your screen. Feel free to do so if you wish.
Okay, I will do it now. Okay, do you see my screen?
Yes.
Okay, so our solution idea passed through 3 stages. They were very fast, so we converged to the final solution very fast. the first idea was obviously to make a trainable model to resample the image. Usually we say upsample because we think about frequency, where you say downsample about space. So our upsample was about making some transposon convolution layer, which allowed the network to learn a way to expand an image. What we thought about this solution was that it was missing some high, let's say, semantical level. So the network was not able to learn at high semantical level. So the first thought was to add a small piece of downsampling. And when we scaled the resolution, we scaled down the resolution, but we raised the semantical level of the information. So we thought something about an unbalanced UNet on which you have a contracting path, which is smaller than the expansive path, and you have this kind of asymmetric U. But then on a third thought, we thought that it was better for us to have an initial deterministic resample of the images to like nearest neighbor, something very simple, and then use a standard UNet, because we could leverage, of course, a lot of libraries and avoid error in implementing an asymmetric UNet. That was the solution we brought forward. So mainly we had, that's the central part of our model. On the pre-processing, we had a model which allowed us to extract feature in a very dynamic way. So we configured a feature name and we use it, each feature as a channel to our UNet. So we did some data cleaning, feature extraction. We resampled all the feature to high resolution using near neighbor. And we had, let's say, a box of images which we could treat as a multi-channel image. The channel could be 3, 5, 10. We tested a lot of variants. And of course, we extracted 2 ground truth. One ground truth was about the area. So it was simply the upscaled version of the original image. And the other ground truth was an image made just of point, spatially positioned correctly spatially, and with a ground station acquisition value. Using this kind of ground truth, the second one I'm talking, and think that we back propagated just the error that we had on the point. So the back propagation was very poor on our model. And initially we had a lot of artifacts because of it, because if you think about it, the spatial information for the error back propagation is steady. So the pattern that is back propagated is always the same for a given area of interest. So initially we had a lot of artifact and noise in our result. But then we joined another loss on our network based on the area ground truth, and that was back propagated for all the image. And also we had a lot of benefit from inserting a lot of data augmentation. Data augmentation allowed us to lose this spatial constraint of a back propagation. So we could back propagate in many of the ways. We could use all the network weights for back propagation. So our model was mainly, as I told you, a UNet receiving a multi-channel input as an X, and an area ground truth and a points ground truth as a Y. Another thing that we did, usually UNet is used for segmentation, so it's performing classification at a pixel level using a final activation like a softmax. Obviously, we removed this softmax activation, and we mainly did what we did was some kind of regression at pixel level. So each pixel was predicted with a UNet. For the strange things, particular things of this challenge was that we had 2 kinds of ground truth that I've talked about. So one area ground truth and 1 point ground truth. And those were somehow not always completely aligned. So I think that in case where we had 2 completely aligned information, the UNet output was everything that we had needed. So the output for the UNet was the output of our solution. But since we had somehow contrasting information between the areas and the points, we added a processing layer which did 2 things: an equalization point and a points equalization and an area equalization. Points equalization mainly means having Gaussians that provides more credibility for the points that are close to ground station position. And area equalization is re-equalizing all the image to, let's say, to constrain it to be close to the area ground truth. And that was super fast, our solution architecture. And then I know that Cristiano has a couple of points to add.
Yeah, thank you, Andrea. Well, I just wish to add that we are going to deploy this processor on WASD, which is our cloud platform for Earth observation. And you can check it out for free on wasd.net. And basically, it is a platform that allows for easy deployment of your processor to the cloud. The nice thing that since WASD runs on diases or dias, as you wish to pronounce it, you can have both the proximity to data and the computational power. So it's very easy to transform your algorithm into a service with that. To develop with WASD, you simply need to use the programming libraries that we provide. They're kind of, you can think of them as a cloud development kit. And then with that, you're ready to interact with the remote platform. And once you're done, you simply need to zip your code and drag and drop it on WASD, and it will be deployed in a matter of seconds. So after this challenge where we had a period of fight, I wish to say open a possibility of cooperation instead. And since we are running many impactful activities with WASD, we are open to new partnership. So if you try it and like it, and we hope you will, we'd like to hear from you and maybe see if we can build some projects together. So check it for free at wasd.net. Thank you.
So before I hand back the microphone to Nicolas, all the winners will receive messages from my colleague Anne-Catherine, and you will be able to start telling us what you would want to claim amongst the prizes in the catalog. And again, you're using that first come, first serve system. That's the only way, because the number of prices for each prize is finite, unfortunately. But again, complimenti, congratulations to the winners and to the number 2 and number 3 and to the student. It's nice to see that some important players also in the conversions of artificial intelligence and Earth observation have found an interest in participating in our challenge. We see it as a real honor, and we look forward to your participation in our second challenge, which will be simpler. So therefore, even maybe more, hopefully, more participants, but still a nice lot of prizes. So, Nicolas, the floor is yours again.
I guess this is for Gregor, right?
Yeah, so I'll give the floor now to Gregor Milczynski. Gregor Milczynski is the CEO of Synergize and one of the founders. They're quite famous in our little ecosystem. I must confess that personally I have the greatest admiration for Grega and his colleagues. He knows it, but I like to repeat it in public because basically Grega with his, first with his Sentinel Playground and then with his EO browser, completely revolutionized access to Earth observation data. So he's done an immense service to the community, and his platforms are used by journalists, scientists, companies, whatever. So really, really an interesting development and something that really changed the face of Earth observation as we used to know it. And he has taken responsibility for the development and operation of this second challenge. So I will, with no further ado, let him introduce it. Grega?
Thank you, Stefane. But just before I start, I thought that there was idea that Christoph will first do some introduction, or have we changed this? I'm happy to go on, but
that who would do the introduction? Oh yes, true. Excuse me. Yes, in fact, yes, we were a little bit carried away. We first, but I have a problem with my view. I don't see the view. I don't see the people anymore. Ah, now back. So yes, indeed, there was an introduction by Christoph von Tricht. Christoph, the floor is yours.
Sure. Yeah, I see that we're running a bit behind on time, but I had the pleasure to talk a little bit about food security, AI, and EO, just to give a very gentle introduction, let's say. So my name is Christoph van Tricht. I'm a researcher at the Belgian Research Institute VITO in the remote sensing unit and the agricultural applications team, where it is exactly where we try to address some food security challenges using Earth observation data. And nowadays, everyone knows artificial intelligence, deep learning plays a bigger and bigger role. So that's why we're also actively looking at that. Giving a bit of motivation for food security is very easy because as of March 2020, we're at 7.8 billion people. That's a lot of mouths to feed. Globally, just expanding agricultural area is not always possible anymore. So the only way to meet the increasing food demands is actually to raise agricultural productivity. And one way to do so is to monitor agriculture from space so that we can actually see what is happening and intervene as soon as possible if we see that something is going on. How would we do that using remote sensing? Basically, I think there's two big things that we can do. One is mapping, and that's just finding out where the agriculture is and where the individual crop types are, what the crop types are. And then as soon as we know where the agriculture is, then the second thing we can do is monitor so that we see how well the crops are doing and if something is going wrong or not. Well, we're an AI algorithm community here. If you see mapping and monitoring, that's basically just classification and regression. And these are the things that we can perfectly do with algorithms from the AI domain. So how would we do something like that? Well, basically, there's a lot of AI ingredients out there coming from the computer vision domain, the pure AI community, and all these buzzwords sipple in through the EO community. But of course, we as EO community also have our ingredients. There's all that free data, for example, out there, some ancillary information, a lot of training samples. And then basically, if you want to address food security challenges, the only thing you need to do is find a good recipe that combines some of these elements. And I think that that's also why we're here today, to find a solution for one of these things, to find a recipe. Just to give you very concretely two examples. So first, mapping, what grows where. Usually, it's not always the case, but 95% of the cases, we do that using a supervised learning approach. And then you need training data, of course. So mapping exercise needs training labels, and often in our kind of challenges, that is the hardest part. And it determines also to a large degree what kind of solution you can develop. If there's not enough training samples or very bad quality, then there's only that much you can do. And if there's a lot of training samples with very good quality, there's much more to be done. So to give a concrete example, in the ESA World Serial project, which is currently ongoing, we need to create a global map at 10-meter spatial resolution of annual cropland and seasonal maps of wheat and maize, also at 10 meters. Now, that's quite of a challenge because the globe is big. There's a lot of different climatologies. There's different levels of agricultural landscape, management practices. So you need to try to bring all of that together into one big exercise to map things at the globe. So yeah, it all starts, of course, with training data. And we see that if we collect training data for agricultural mapping, there's actually 3 basic groups, and that's point labels, just GPS location and let's say the crop type. Then there's polygon labels that we know the agricultural boundaries, and sometimes we even have a full mask. Now you can see already, depending on which of these training samples you have more or less possibilities to go into the more advanced artificial intelligence algorithms or not. And so, yeah, if we try to collect that to build something that works globally, yeah, there is no training data that covers the entire planet. So you see here that we try to group some zones across the world to try to distribute training data as much as possible. But still, there is a lot of empty regions where you don't have anything. So the only thing that you can do then is try to come up with an approach where you build on the global training data and where you try to extract as much as generically as possible features from the satellite input, and then train that on the available training data that you have. And then hopefully in some local regions where you have the more specialized training data, you can actually take that model, do some transfer learning, fine tune it, so that you come up with an approach that works everywhere. If you have local training samples, it's a very specialized version of the algorithm. If you don't have it, then it's only the generalized model, but at least it's something. And then you see here in the example left, that's schematically basically what we do usually in the high level architecture. So we take all these remote sensing data sources and the ancillary data sources, and we do some sort of encoder decoder structure to come up with finally your classification, in this case, whether it's cropland or no cropland. And just to give you an idea, so we try to go actually for let's say convolutional neural nets, convolutional recurrent neural nets, but because so many of the training samples were only points, there wasn't much to do there because we often lacked the context. But then it turned out that even with a pixel-based recurrent neural net approach, if you do some good pre-processing and really making use of the advantage that in remote sensing you have that temporal dimension, that we were already able to get very nice and smooth output classification maps, and that we even didn't really need the convolutional step here. And that's basically really the recurrent step that worked. Also in some more remote areas like Kenya, where we don't have a lot of training data, it turned out that with this transfer learning that we were able to get some good results there too. Just from our point of view, some mapping lessons learned, I think it's always very important to know what your inputs are, if you need to do pre-processing or not, if you think your algorithm can take care of noisy inputs or not. That's to be decided. The nature and the abundance of the labels, I think, also dictates how fancy you can go. I mean, it's at a crazy speed that the AI algorithms are being invented, but we only can do that much within the EO domain. So really look at what your data is that you need to start from. And of course, also a satellite image, that's not just another picture. So we have a lower spatial resolution generally, but we do have a higher spectral resolution, and we have that temporal dimension. So really the multiple acquisitions is a huge asset that we need to learn how to use if we apply some deep learning. And then, yeah, also robustness and transferability. That's to me the real challenge. You can develop something very locally, but please, from the start, we always need to think about, can we upscale this? Can we also apply it somewhere else? Because then it becomes really useful. That brings us then to the second step. Once we know what is there, can we also monitor it? And in food security, how we usually monitor with remote sensing is by looking through the growing season, whether a crop is doing fine or not. So that's some sort of a greenness, for example, that we look at. And then how much we deviate from the normal situation, the anomaly that we detect, that is then information that we can feed to the farmer, let's say, so that he can see whether he needs to water his plants or that he needs to prevent a further disease outbreak. So this all works quite well. It uses optical data from Sentinel-2, for example, but usually, yeah, we know that 67% on average, the globe is covered by clouds, and then we have a huge problem. That's probably the most well-known problem in the EO community for a very long time already. But now with AI coming into place more and more, many of us are starting to look at different ways to get rid of the cloud artifacts. And so this image here is from optical. And if we overlay, for example, a radar image, then we see that we can exactly look through clouds, which is a very nice thing. But on the other hand, a radar sees something completely different than optical. There is correlation, but it's highly nonlinear. yeah, within an AI community, if you hear correlation but highly nonlinear, that's like a huge opportunity to apply machine learning to that. So that's what is being done now more and more. So feeding the radar information into the optical, and in this case now we are at a regression step, not only a mapping step. And then we start, for example, from a noisy cloud obstructed input time series of greenness from Sentinel-2. We feed in radar information, which is not obstructed by clouds. And then a recurrent neural network could figure out the correlation between the two and actually spit out a cloud uninterrupted fused time series of that greenness. That's for the time series level, but nowadays we also expand that to the image time series level, time series level. There's many ways to do that. We have tried, for example, a conditional GAN approach, where we actually not only look at time series, but really spatial temporal cubes of Sentinel-1 radar and Sentinel-2 optical. And then the generator is actually going to fill in the clouds to produce cloud-free estimates of that. And the nice thing about regression in Earth observation is that you don't really need training samples from on the ground, and that there is an endless amount of training samples available. Every time you have a radar and optical acquisition, you have a training sample available. So that's really nice. And just to let you see what it looks like. So this is what an optical image looks like if there's clouds. And so that's an NDVI, that's a greenness indicator to monitor the fields. And then if you do the fusion step on top of it, which is being aided by the history of the cloud-free optical, because we need that as well. And then, of course, also the cloud-free radar images, then we are able to in-paint, of course, these cloudy gaps. Now, there's a few important things there also to take with you, and that is, yeah, okay, you can fill in gaps of images, and it looks nice, but yeah, of course, we need to look beyond the pretty pictures. And if we in-paint the cloud, then it is also important that what we estimate with AI is also what is happening on the ground. Otherwise, it looks nice to a farmer, but it's not realistic. So that's something to be very careful about. The need for explainable AI is therefore also bigger and bigger nowadays. Also to take in the people that are maybe not too much into AI. They always say like AI is a black box. No, it's not a black box. It's just a whole bunch of different mathematical equations, and you need to track how the information is flowing, and their explainable AI can maybe help us and also convince some other people that the AI is doing some smart stuff. And then, yeah, of course, we have huge remote sensing data sets. We need to do it also regularly if we have some sort of service. So we need to keep an eye on the expensiveness as well. If we have a neural network which is 2 gigabytes in size, takes 5 minutes to load on a node, and if we then need to apply it in real time, that's many of the IT guys don't like to hear us coming in that case. And so basically what I usually see is that in Earth observation, to me, it is more important to tailor a solution to Earth observation starting from a rather simple model than to take always the latest neural network architecture that has been published in the computer vision domain and then just blindly apply it to remote sensing. Because yeah, EO is a domain in itself. We cannot just take everything from the computer vision domain and just apply it like that. Having said that, I think deep learning is very powerful for multi-sensor classification and regression tasks. But yeah, we do need some healthy skepticisms to see what we are doing, what the inputs are, what the expected outputs are. And that's why I think that the best neural nets are probably not the most complex one, but yeah, probably the models that are more tailored to the remote sensing challenges that we face today. I think that is the real challenge there. So basically, I'd like to end with the sentence I started with. I think both from the AI and the EO side, all the ingredients to face, let's say, the food security challenge in this case are there. And so the real challenge that we're facing today is to find a good recipe to solve at least a part of that challenge. And with that, that's all from my side, Grega.
Thank you, Christoph, for a very insightful kickoff to this. Grega, now your turn.
Yeah, just to see if I'm the... Yeah, so you should see my screen, right?
Yes, we do.
Oh, very well. So I'll just go into the topic so that we spare time. Christoph has nicely explained all the challenges of the crop-related machine learning technologies. And now we actually want to tap into some of this, not everything that was discussed, but some of this. Specifically, we want to make use of the Sentinel time series for feature enhancement. So, so we know that Sentinel-2 is a 10-meter resolution, and we've seen quite some examples of Sentinel-2 being applied to the like super resolution technology so that it looks nicer, right? But we don't want to go there. We actually want to make use of these and similar technologies to actually enhance the features that we get from that, and we want to focus on the features related to the land management. So what essentially we want to do is take Sentinel-2 time series at 10-meter resolution, as it is natural, and then create a arable land cover dataset at 2.5-meter resolution out of this. Now, how we go there? So inputs are Sentinel-2 level 2A data. For 2019 season, we applied it there. We were looking into March to September, which is where most of the agricultural activity is happening. We provide all multispectral bands, and to make it easier for people which are not Earth observation experts, we interpolated 20 and 60-meter resolutions to 10 meters so that we have everything at 10 meters. And in addition to the spectral bands, we add the sync classification and the S2 cloudless cloud mask. So you have a couple of options to try to filter out the clouds so that you can just try to make use of all of them, or the ones that are most relevant. And now the output, as mentioned, is a binary mask which says this part is cultivated or not at 2.5-meter resolution. And I mean, cultivated means that there is that is actually agricultural activity happening there, like greenhouse would not be that, because greenhouse is just a greenhouse, right? There is no visible agricultural activity there. Now, to evaluate the results, we will simply do the pixel overlap with the ground truth data. We will weight the parcels based on how small they are. So, I mean, the smaller parcels have the higher weights, which means that the more precise that you get, the better results you'll get with the small parcels. But obviously, the solution needs to work with the large parcels as well, right? Because we want to have all the parcels available. So the area of interest is here in Slovenia. We have created 100 boxes for training, which is a lot of data. And then there are additional 25 boxes that are used for testing. We don't reveal where these testing boxes are, so that people don't go and try to overfit it. And now, similarly as with first challenge, there is an automatic process which evaluates the results so that you can get update feedback on how good you are. We have a public and private leaderboard so that you can test yourself, but then the final evaluation is done on the boxes that you don't know which they are. Now, there are some rules in place. So first of all, you only need to use the data that we provide, meaning Sentinel-2 data and obviously the labels that we will provide. No additional data is allowed, and we don't allow pre-trained models as well, for the same reason, because we don't want that we get some fine-tuned models that are not kind of visible and understandable. And we will ask for the code so that we can reproduce the results at the end. So for the winning solutions will be checked so that we know that they are compliant with this, the rules that are mentioned here. To make it easier, to try to make this challenge interesting to also non-EO experts, we went one step further this time with the challenge 2 to make it possible to actually run it in the pre-provided cloud. So altogether is about 16 gigabytes of data, so it's not that much. You can download this via APIs, or you can simply download the data as a package. We have the Jupyter notebook prepared, which where you have all the steps on how to download the data, how to visualize. So all these things that are typically need the Earth observation know-how, even the submission example, so that you really can focus to the machine learning part. And also, if you want, there is a hosted workspace environment on the Eurodata Cube with some GPU power so that you can run this there directly in the cloud. If you prefer, or if you have your own environment that you like more, there is a Docker there which you can simply download and use on your own resources, simply to make it easier, right? So you don't need to use this starting pack, but you can to just be more efficient in the core task. Now, this is just an overview of how the Jupyter Notebook look like. So you go through all these steps on how to analyze and evaluate the data and all the results, analyzing the results and so on. So to conclude, we really want to make use of the enhanced resolution of Sentinel-2 to get actual results, not just beautiful images. There are cloud tools available if you want to use them. If not, no problem at all. The challenge 2 starts today, and there is time to submit until September 30th. We don't expect that it will take this long, but because there is quite some vacation, probably everyone looking forward in these coming months, we wanted to have a period long enough so that everyone really can participate. So I just also want to use this opportunity to thanks to Technical University of Munich and DLR because they provided quite some cooperation to define the challenge. Thank you very much. And I'll conclude here and back to you, Stefan.
I was on mute. Thank you, Grega. So the challenge, the second challenge of AI4EO is now open. You can directly go after this webinar to our AI4EO.eu website, where you will see the challenge 2 is active, the data is there, it's hopefully well documented, the catalog of available prices at this point is already there, the rules, the leaderboard, the forum, etc. So it's actually open. So